Hello, Assalamu alaikum. So this lecture is the continuation of the previous video lecture, which was on Introduction to Machine Learning, where we discussed unsupervised learning methods with respect to the continuous and discrete data. Now in this lecture we are going to focus on supervised learning methods, probably more like which works towards the discrete data. So we are not going to explore regression methods, but we are going to explore the categorization or classification method, which are used under the umbrella of supervised learning. So as discussed, we'll consider the classification or the categorization approach, which can take into account the discrete data. So ImageNet, we already discussed in the previous class that it has images with respect to the 1,000 classes, 1,000 categories, and the database contains 1.2 million images and approximately 100,000 of test images. So if you look at a recent 5 or 10-year history of machine learning, one of the reasons that learning algorithms work so much better now than even say 5 years ago is just the sheer amount of data that we have now and that we can train our algorithms on. ImageNet is image database organized according to the word net hierarchy, currently only the nouns, in which each node of the hierarchy is depicted by hundreds and thousands of images. Currently, ImageNet has an average of over 500 images per node. You can check more details on the ImageNet on the paper which have been uh, uploaded on arXiv in 2012. The title of the paper is ImageNet Large Scale Visual Recognition Challenge. Now, most probably what we do with the training data is not the training data, but the overall data is that we split them into three uh, sets basically. One is the training image set, second is the validation image set, and third is the testing image set. So training data is the actual data set that we use to train the model, like updating weights and biases in the case of a neural network. The model sees and learns from this data. Validation data is derived from the validation set, which is used to evaluate a given model, but this is for frequent evaluation. We as machine learning engineers use this data to fine-tune the model hyperparameters. Hence, the model occasionally sees this data but never does it learn from this. We use the validation set results and update higher level hyperparameters, so the validation set affects a model but only indirectly. The validation set is also known as the dev set or the development set. This makes sense since this data set helps during the development stage of the model. Now another important set is the test data set, and this set provides the gold standard used to evaluate the model. It is only used once a model is completely trained using the trained and validation sets. The test set is generally what is used to evaluate competing models. For example, on many Kaggle competitions, the validation set is released initially along with the training set, and the actual test set is only released when the competition is about to close. And it is the result of the model on the test set that decides the winner. Many a times, the validation set is used as the test set, but it is not good practice. The test set is generally well curated. It contains carefully sampled data that spans the various classes that the model would face when used in the real world setting. Now that you know what these datasets do, you might be looking for recommendations on how to split your dataset into train, validation, and test set. This mainly depends on two things. First, the total number of samples in your data, and second, on the actual model you are training. Some models need substantial data to train upon, so in this case you would optimize the larger training sets. Models with fewer hyperparameters will be easy to validate and tune, so you can probably reduce the size of your validation set. But if your model has many hyperparameters, you would want to have a large validation set as well. although you should also consider cross-validation. Also, if you happen to have a model with no hyperparameters or ones that cannot be easily tuned, you probably don't need a validation set too. All in all, like many other things in machine learning, the train set, test set, and validation set split ratio is also quite specific to your use case, and it gets easier to make judgment as you train and build more and more models. So it's an iterative process. Now, this is a kind of a traditional pipeline, machine learning pipeline for training the images. So once you have the training images that in your training set, you extract the image features from them, and these image features will be the input to the training set, and of course with their corresponding labels, because the training set have images, so image should have a corresponding label to it, which is an input to the training of classifier, which we will discuss in this lecture as we move along. And then once the model has been trained, we get a trained classifier. Now for testing phase, we have an image which was not available in the training set. So what we will do is we will continue the same pipeline. We extract the image features, we apply the trained classifier which has already been trained, and we will perform the prediction. Now classification problems in image and signal analysis require, on the algorithmic side, to take into account complex information embedded in the data. Images might contain many thousands of pixel values in several color channels. Their correlation and relationship characterizes the class and enables drawing a separation criteria from other classes. We have already discussed these things in our previous lecture videos, and also the lectures which have been taken physically when there was no pandemic, when the, the current situation has not been arised, when we used to take our physical classes. So we have already discussed these things earlier on. It is generally known feasible to integrate all this information in reasonable running time for classification problems. Therefore, image and signal features are extracted as representatives of each object and its class. These features, be they boundary representation like Fourier descriptors, Harris corners, or Gaussian-like peaks, form a lower dimension representation of the object and fall within a characteristic region in the feature space. Hopefully, differentiated enough from objects in other classes, but similar to objects of the same class, image features are, loosely speaking, salient points on the image. Ideally, features should be invariant to image transformations like rotation, translation, and scaling. In the context of classification, features of a sample object image should not change upon the rotation of the image. Changing scale, tantamount to resolution change or magnification, or changing acquisition angle. However, these invariances are not without a limit. Furthermore, features should be insensitive to lighting conditions and color unless specifically required. Well-known examples of image features include corners, shift, surf blobs, and edges. Not all of them fulfill the invariances and insensitivity of ideal features. However, depending on the classification task and the expected geometry of the objects, features can be wisely selected. For example, on a PCB board which embodies well-defined geometrical shapes, corner features might be a good starting point. Harris corners computes the 2D eigenvalue of the Hessian of the image, partial derivatives calculated convolving the image with Gaussian kernel, and according to their value determines a cornerness metric, object characterization by a combination of feature points and their associated descriptors is also a common practice. Because features like peaks and edges focus on one aspect of the object, whereas surf and binary features shed light on another aspect, newly examined image, in which the object might appear in arbitrary pose, should be naturally characterized by any possible means. It is then the responsibility of the algorithm developers to make sense of the extracted features value. type and their relationship in order to tailor a classification process. Now we have already discussed some of the features which we can extract. We have discussed about surf. We have discussed about histogram of oriented gradients. We have like talked about corners in details, and there are others such as local binary patterns and LPQ, and there are other feature extraction methods which are already available in terms of packages which you can use directly with just one line of code. So these are the features which could be used for this traditional pipeline of machine learning for this particular step, which is image features. Sometimes it is also known as feature extraction step. Now features can include raw pixels, features can include histograms, features can include templates, features can include SIF descriptors, which we have already discussed. We have already discussed about histogram of gradients, but we have not discussed about gist and of. But you can check the documentation of OpenCV or MATLAB, as they are already available in their repositories or in their built-in packages. Now, if there was a data science hall of fame, it would have a section dedicated to labeling. Now, once we extract the features, we also have to provide labels to the training classifier or the training method to build a trained classifier so that it could be used for testing phase. Now, of course, in testing image, we do not provide the labels, but we do have the labels so that we can evaluate our method against uh, we evaluate the method against the trained classifier. So it's like we evaluated how well our classifiers perform on unseen data, and that would be possible if we have already a kind of a label or human expert to back that back that classification result up, so that we know that how well a trained classifier performs on an unseen image. The labeler's monument could be Atlas, holding that large rock symbolizing their arduous, detail-laden responsibilities. ImageNet, an image database which we have already discussed about, would deserve its own stele. For 9 years, its contributors manually annotated more than 14 million images. Just thinking about it makes you tired. While labeling is not launching a rocket into space, it's still serious business. Labeling is an indispensable stage of data preprocessing in supervised learning. Historical data with predefined target attributes values is used for this model training style. An algorithm can only find target attributes if a human mapped them. Labelers must be extremely attentive because each mistake or inaccuracy negatively affects a dataset's quality and the overall performance of a predictive model. And this is very sensitive. This is a very sensitive issue in especially the medical image processing or medical image analysis field. How to get a high quality labeled data set without getting gray hair? The main challenge is to decide who will be responsible for labeling, estimate how much time it will take, and what tools are better to use. If there was a data science, uh, it's like uh, of course, there are some methods which are dedicated especially to to use limited labels from a particular data set. Like if you consider transfer learning, or if you consider a kind of active learning approaches, more of like semi-supervised learning approaches. So basically, they are designed in such a way to kind of relieve the pressure from human experts to label the data, so that we can use a limited amount of label set, and then we train a classifier in such a way that the model should label the other samples in the data set. So it's a kind of a think pair share strategy, where think is a kind of a teachers begin by asking a specific questions about the text. The students think about what they know or have learned about the topic. Pair is like pairing each student with another student or a small group, and share is that they share their thinking with their partner. So it's a considerable strategy when we consider labeling and we consider recognition tasks in supervised learning approaches. So considering that, what are the possible supervision label types to consider? Let's see one example. So images in the training set must be annotated with the correct answer that the model is expected to produce. Now this image contains a motorbike, but you can label it like this. But remember, it also have a kind of pixel values which belong to the background and which belong to another object category, if you may consider, like the road. And this is one of another example to actually make it more specific or make it more kind of less inclusive of the of the background pixels and the other object category pixels. And also you can just consider different parts of this particular object to be considered for as and could extract it as a features and label it separately. So you can label that this is particular the front part, these are the tires, the front tire, the back tire, this is the back seat, and this is the engine or something. And if they all occur in one image, then you may consider that this belongs to a particular object, which is a motorbike. So there are different strategies to label the or different strategies to annotate the object in an image. And there are several actually what you say is packages or several platforms which are available for annotating the image data. In MATLAB there is a specific API or a specific application which is the object or image annotator, and there are other image annotating APIs in Python or in other languages like OpenCV, so that you can use them for annotating the object in an image with respect to your custom dataset. Now in supervised technique or in machine learning, as we say, the spectrum of supervision is actually very diversified. We have already discussed about unsupervised, that we do not have any labels in unsupervised learning. For weakly supervised, this refers to a problem where you have labeled data, but the labels aren't quite right. It might be that there's noise in the labeling process, or it might be that the labels tell you which of a collection of classes are given or a given observation belongs to. The goal is to produce a classifier that accurately outputs the labels given this less than ideal input. So in this case, if you will see, you are just given the bounding boxes, of course with respect or with the inclusive of other object categories or background pixels, or in this case you are given some small regions which are actually attached to, let's say, some other objects which are very much attached to some other object. So in this case you will see that eyes, nose and mouth, so these are different object categories, but they have the same color pixel values as of your face. So in this case it's very difficult, or this is not a kind of what you say is ideal input which you may provide to the supervised learning algorithm. But this is a kind of a challenge for machine learning engineers to design a method which could still identify or which could still recognize the objects on in the test set while provided with these kind of image labels. So these the algorithms which lie under the category of these particular labeling strategies are weakly supervised, and mostly weakly supervised techniques are considered to be more optimization methods, because you need to optimize the methods with respect to other losses to overcome the limitation of the labeling capability which has been done while annotating the images. So it's more of like kind of optimization. It's more kind of like employing optimization strategies to overcome the limitation of labeling the images in a certain way which have been provided in the training data set. For now, for the fully supervised, of course, each and every object has been annotated quite it's like in a specific manner. Now there is another category of this which is semi-supervised learning. Learning which aims to label unlabeled data points using knowledge learned from a small number of labeled data points. So basically, if you will look in active learning methods, so basically active learning methods or active learning is one of the field which deals with semi-supervised learning strategies that they consider a small amount of labeled data. They get the most informative instances or most informative label instances to train their model, and based on their training they label other instances in the training data. And also there are transfer learning approaches in which there is a source data set which has the labels and the target data set which does not have the labels. So you use the information from the source data set and assign the labels to the target data set accordingly. So if we ask questions, is it a good training example? Or if we look at the labels which we provide, so is it a good label? And some of the labels or some of kind of generated sentences from this is an elephant standing on top of a basket being held by a woman, or a woman standing holding a basket with an elephant in it, or a lady holding an elephant in a small basket, a lady holds an elephant in a basket, an elephant inside a basket lifted by a woman. So basically these all can be labels to this diagram. Even if you go to a granular level, you will see that what type of objects has been recognized in this image. We have recognized an elephant, we have recognized a human, we have recognized chairs. So all these objects have been recognized in this image, and these are the labels which are actually generated based on this image. But how good are these labels? So let's see what the Google returns with the search when using the first caption, that is an elephant standing on top of a basket being held by a woman. So if you consider this, Google returns these results. So you get this result, you get this result, and you get this result. So you can understand that how good the caption was or how good the label was generated. Here you will not see any human which is holding an elephant in a basket. So you can see that how good a label is for that particular image by trying different labels to it, like trying different labels and see if the Google returns some of the similar images with respect to the image which has been shown here. Now, an elephant standing on top of a basket being held by a woman, if you will just write it on a platform which is wordsi.com, you can see that what NLP, the natural language processing, the combination of natural language processing, computer graphics, and simple labeling would do. And you can see here that some chairs are generated. Of course, you can just vary the appearance of chairs, you can vary the appearance of background. You should visit wordsi.com. I will show you some examples which can be generated from label descriptions, but it is a kind of a powerful tool that what a simple labeling could do if you consider the combination of computer graphics and natural language processing to generate such images from the labels. And you will see that how close they are to your actual labeling which you have already assigned to an image for training a classifier. So these are some of the examples which have been generated with the help of sentences. So this is one of the example, and I urge you to visit wordseye.com. It is a good platform to help you understand that how labeling can actually help you or help the computers in understanding the context, or in understanding uh, in make you understand that how the classifiers actually learn those labels within the context of image processing and computer vision. So this is one of the examples. There is another example. The elephant fits in the purple bird cage. The bird is on the cage. The ground is pale yellow. Okay. And of course, there are some other examples which are like this. Now let's consider the same traditional pipeline. So the process of training an ML model involves providing an ML algorithm, that is the learning algorithm, with training data to learn from. The training data must contain the correct answer, which is known as a target or target attribute. So we are talking about this particular block. The learning algorithm finds patterns in the training data that map the input data attributes to the target, the answer that you want to predict, and it outputs an ML model that captures these patterns. So the trained classifier should be able to generate a function which, if provided with a particular image, can produce a certain label or can produce a certain answer. So when we apply a prediction function to a feature representation of the image to get the desired output, so if we have this image, if we extract the image features and give it to the trained model, then we assume that we get this output from the trained classifier. Similarly, for this image we want to get this output, for this image we want to get this output. So basically I think this arrow has been misplaced, so the output label is actually Y, the prediction function or classifier is F, and the image feature is X. So given a training set of labeled examples, which is a pair of image and label, X is the image or the feature, Y is the label, we want to estimate the prediction function F by minimizing the prediction error on the training set. And the testing phase is to apply that particular function to an unseen test example and output the predicted value to classify X, which should be the same as the actual label. So if it is not the same as the actual label, then there is no point of training. So you have to train it again. You have to think of different parameter optimization or different hyperparameter tuning to improve the performance of the trained classifier, and we will discuss some of those in this lecture video. Now for classification, what we want to do is we want to assign the feature to one of two or more classes, depends on the number of categorizations we provided in the training set, and a decision rule divides input space into decision regions separated by decision boundaries, literally boundaries in the space of the features. Now one of the classifiers is the nearest neighbor classifier, and if you can look at the training examples from class 1 and class 2, if you have a kind of a test example, you will see that it will calculate a kind of a label of the training example which is nearest to this test example. All we need is a distance function for our inputs. There is no training required. But there are many variants to nearest neighbor classifier. So the principle behind nearest neighbor method is to find a predefined number of training samples closest in distance to the new point and predict the label from those. The number of samples can be a user defined constant like k nearest neighbor learning, or vary based on the local density of points, which is also referred to as radius based neighbor learning. The distance can in general be any metric measure, like standard Euclidean distance is the most common choice. Of course, you can use Manhattan distance, city block distance, and the Jacquard distance, and more. So the neighbors based methods are known as non-generalizing machine learning methods. since they simply remember all of its training data, possibly transformed into a fast indexing structure such as ball tree or KD tree. Despite its simplicity, nearest neighbors has been successful in a large number of classification and regression problems, including handwritten digits and satellite image scenes. Being a non-parametric method, it is often successful in classification situations where the decision boundary is very irregular. Now, for by visualizing this, what we want to ask question is, what does the decision boundary look like in this case? Now, this is one of the example of decision boundaries. That's what I said, that a decision rule divides input space into decision regions separated by decision boundaries. So this is a decision boundary which separates region 1, region 2 and region 3. So the samples, if they are closer to region 3, then they would be classified as region 3. The samples which are closest to region 1 will be classified as region 1. And this is a kind of an example in terms of Voronoi diagram, which divides the input space into decision regions separated by decision boundaries in terms of Voronoi partitioning. Now, another variant which of the nearest neighbor is the k nearest neighbor, and KNN algorithm assumes that similar things exist in close proximity. In other words, similar things are near to each other. So in this case, if you have this plus sign or this plus sign near green zone, so it will be assigned to red and green respectively with respect to one nearest. But if you consider the three nearest, of course it will take the three samples. So maybe the assigned label would change if you consider more, like 5 nearest or 3 near or even 7 nearest. So it is also known as birds of a feather flock together. It is widely disposable in real life scenarios since it is non-parametric, meaning it does not make any underlying assumptions about the distribution of data, as opposed to other algorithms such as Gaussian mixture models, which assume a Gaussian distribution of the given data. We are given some prior data, also called training data, which classifies coordinates into groups identified by an attribute. I would recommend that k can be kept as an odd number so that we can calculate a clear majority in the case where only two groups are possible, for example red, blue. With increasing k, we get smoother, more defined boundaries across different classifications. Also, the accuracy of the above classifier increases as we increase the number of data points in the training set. Simply a good one to try first. With infinite examples, 1NN probably has error that is at most twice Bayes' optimal error. Now there are also linear classifiers which finds a linear function to separate the classes like this. A popular class of procedures for solving classification tasks are based on linear models. What this means is that they aim at dividing the feature space into collection of regions labeled according to the values the target can take, where the decision boundaries between those regions are linear. They are the lines in 2-dimension, planes in 3-dimension, and hyperplanes with more features. I will not go into the details of some machine learning algorithms, but abstract details of some of them could be found in the hidden slides of this presentation. You can download the slides from Google Classroom. Of course, it would take a whole lecture to make you understand a single machine learning algorithm and the maths behind them. So I'll not go into the details of them. Now, one of the very popular machine learning algorithm is the logistic regression, which actually maximizes the likelihood of label given data, assuming a log linear model. And now this is particular the log linear model, which you can see here, and the logistic regression is a kind of more of known by the function which it uses, which is sigmoid function. So a sigmoid function is a kind of let me draw it here. So it's a so so sigmoid function is like this. So it's like this is kind of a rising trend from minus 0.5 to 0.5, and as it goes further it will just be stabilized to 1. So basically you can just kind of a cutoff here, with a static like a static threshold, that if it is greater than this it belongs to this class, and if it is less than this it belongs to this class. So basically this is the way to categorize uh, the labels or the samples using logistic regression. So this is an example of a sigmoid function. The logistic regression is another technique borrowed by machine learning from the field of statistics. Logistic regression is a statistical model that in its basic form uses a logistic function to model a binary dependent variable that is used to model the probability of a certain class or event existing, such as pass fail, win lose, alive dead, or healthy sick. This can be extended to model several classes of events, such as determining whether an image contains a dog, a cat, lion, etc. Each object being detected in the image would be assigned a probability between 0 and 1 with a sum of 1. It is a mathematical function having a characteristic that can take any real value and map it to between 0 to 1, shaped like the letter S, which I showed you. The sigmoid function, also called a logistic function, outputs a probabilistic label confidence. Now, this algorithm heavily relies on its regularization function, and I would suggest you to use L1 regularization because it also performs feature selection and it is robust to irrelevant features, but of course it is slower to train. Now you can find one of the implementation of logistic regression from this particular link, and it will also explain the bias variance trade-off, which we are going to discuss in this lecture video. Now another popular classification algorithm is linear SVM, support vector machine, which finds a linear function to separate the classes with respect to the weights and biases. Now how? Let us first talk about the support vector machines. So it is a supervised machine learning algorithm which can be used for both classification or regression challenges. For the one which is used for regression is also known as support vector regression. However, it is mostly used in the classification problems. In the SVM algorithm, we plot each data item as a point in n-dimensional space, where n is number of features you have, with the value of each feature being the value of a particular coordinate. Then we perform classification by finding the hyperplane that differentiates the two classes very well. Now we will talk about this hyperplane a little more in the next slide. So basically the support vectors are simply the coordinates of individual observation. The SVM classifier is a frontier which best segregates the two classes, hyperplane or the line. Now how can we just distinguish between these two classes? Uh, I think there is a problem with this particular arrangement. So let's just ignore it. I'll explain you. So what we do is we define the hyperplane, which is tx minus b equals to 0, where t is the tangent to hyperplane. And we want to minimize this t subject to tx minus b to produce correct label for all x. Now above we got accustomed to the process of segregating the two classes with a hyperplane. Now the burning question is, how can we identify the right hyperplane? Don't worry, it's not as hard as you think. So let us see the first scenario, the right identify the right hyperplane. Okay, let me just show and just Sorry for this mismanagement. Okay, let me just show you this image first. This one. So what do you think that which hyperplane is good for these kind of images, or let's say for suppose this image, which hyperplane is good for separating these kind of images? Just let me delete all this. Put it. So sorry for that. So let's see, we have this kind of image, right? Now here we have three hyperplanes A, B and C. Now identify the right hyperplane to classify star and circle. You need to remember a thumb rule to identify the right hyperplane. Select the hyperplane which segregates the two classes better. In this scenario, hyperplane B has excellently performed this job. Now let's say that we have three hyperplanes A, B and C, and all are segregating the classes well, as shown in this image. Now here maximizing the distances between the nearest data point, either class, and hyperplane will help us to decide the right hyperplane. This distance is also called as margin. So if we see this snapshot, we will see that which hyperplane has the largest margin between these two classifiers, and we will conclude that plane C is high as compared to both A and B. Hence we name the right hyperplane as C. Another lightning reason for selecting the hyperplane with higher margin is robustness. If we select a hyperplane having low margin, then there is a high chance of misclassification. Now this is why actually the SVMs are also called large margin classifiers. Now let's see another example. So here identify the right hyperplane. Now the rules as discussed in previous examples to identify the right hyperplane, some of you may have selected the hyperplane B in this case, as it has higher margin compared to A. But here is the catch. SVM selects the hyperplane which classifies the classes accurately prior to maximizing margin. So here hyperplane B has a classification error and A has classified all correctly. Therefore, the right hyperplane is particularly A. Now, if we have a certain kind of, let's say, in this case, let me draw something. So let's say in this case, if I just draw a star here, let me do it in a good way because ink color should be the same as, let me draw. So if we have this kind of a scenario, so here I am unable to segregate the two classes using a straight line, as one of the stars lies in the territory of other circle class as an outlier. As I have already mentioned, one star at other end is like an outlier for a star class. The SVM algorithm has a feature to ignore outliers and find the hyperplane that has the maximum margin. Hence, we can say SVM classification is robust to outliers. Now, another example is, let us think of it like, okay, let us think of like this. So we have something like this, and let me choose a different ink color. So there are some circles here, and let's let's say we have some stars. So in this scenario, we can't have a linear hyperplane between the two classes. So how does SVM classify these two classes? Till now, we have only looked at the linear hyperplane. So SVM can solve this problem easily. It solves this problem by introducing an additional feature. Here we will add a new feature like second order degree polynomial, that is z equals to x square plus y square. So now if we plot the data points on x-axis and z-axis, the points to consider are like this problem will be represented in such way, like, sorry, let me use the same convention so it will be easier for you to grab the point. So if we have like this, and what it will do is it will just arrange the circles like this and the stars like this. Sorry, I am using mouse, so my drawing would not be as good as it is by hand. So similarly like this. So in this case, we actually can just make a good hyperplane like this. So it consider the hyperplane. Consider the design of a hyperplane in higher dimensions. Like if you have a kind of a paper and you draw a line on this, so it's okay. But if you have a kind of non-linear example, so what you can do is you can just fold the paper, and as you fold the paper, you actually are representing your problem in a higher dimension. Now when you fold the paper, your line, the straight line, looks a curve. Now in this curve, you can actually break down a linear problem, like a non-linear problem, into linear problem. And as you fold it more and more and more, you will project that particular line into higher dimensional spaces. And as you go into higher dimension, it will be easier for you to break down into linear classification problems. So that's how the hyperplane actually works. Okay, let me just erase all this and proceed to our next slide. So for nonlinear SVMs, datasets that are linearly separable work out great, like boys versus girls, or like if you have age less than 10 or greater than 10, something like that. These are linear classification problems. But what if the dataset is just too hard? We can map it onto a higher dimensional space, as I already told you that how we can use an example of a line drawn on the paper, and we can just hold it to project it onto a higher dimensional space. So this is an example of mapping it to a higher dimensional space and transforming this non-linear problem into linear classification problem. So what we want to do is we want to map the original input space to some higher dimensional feature space where the training data is separable. So for nonlinear SVMs, the trick is to use the kernels. The kernel trick is, instead of explicitly computing the lifting transformation, define a kernel function k such that these are basically, sometimes they are also called as Gaussian functions, or sometimes they are also called as like spreads. So this gives a non-linear decision boundary in the original feature space. But remember, we only transform the distance function k. Common kernel functions also include radial basis function kernel, or you can define your own user-defined kernel. You can just find out more details on the kernels in this particular book, a tutorial on support vector machines for pattern recognition, or there is another book from Duda and Hart, which is on pattern recognition. But one thing here is to be noticed that a kernel to be valid, the kernel function must satisfy Mercer's condition, that the kernel must be equivalent to a dot product in some space. Now you can check a particular answer to a question at Quora, that why should a kernel function satisfy Mercer's condition, and you will get more appropriate answers. But just to define it briefly, in practical terms, satisfying Mercer's condition means the kernel matrix is positive semi-definite, which means that the underlying quadratic problem for the SVM in dual form has a unique global optimum. In theory, kernels which fail to satisfy the Mercer's condition are not legitimate dot products in some higher dimensional space. So it is very difficult to represent them in higher dimensional space and at the same time just define a linear separable decision boundary to separate those data points. Now also you can use the kernels for bags of features. Of course this is an additional information. So you can use the histogram intersectional kernel, which looks like this. I'll not go into the mathematical details as it will take a lot of time, and we have already crossed more than 40 minutes. So there is another which is generalized Gaussian kernel, which looks like this, and there is for the distances you can actually use Euclidean distance, chi-square distance, and many other distances. And for further detail you can just check out the paper Local Features and Kernels for Classification of Texture and Object Categories. Now how to deal with multi-class SVMs? Unfortunately there is no definitive multi-class SVM. In practice, we combine multiple two classes SVMs. It's like defining a one hot encoding vector. That's the same with one versus others. So training for learning an SVM for each class versus the others, and for testing, apply each SVM to test example and assign it to the class of the SVM that returns the highest decision values. Of course, you can do one versus one, so you have to train for each of those. We have to train a classifier SVM classifier for each pair of classes, and for each learned SVM we have to vote at the testing stage to get a definitive category, the predicted category or classified category. Now, of course, there are advantages and disadvantages to SVMs. The advantages are many publicly available SVM packages. This is a kind of not an advantage anymore, because you can find the implementation of all the classifiers at in some way or another available at many platforms. And kernel based framework is very powerful, flexible, because kernel trick is one of the techniques that has been used extensively in traditional machine learning pipeline to achieve a good classification performance. SVMs work very well in practice even with very small training sample sizes. Now the disadvantage is there is no direct multi-class SVM and you must combine two class SVMs. The computation memory, because during the training time we have to compute the matrix of kernel values for every pair of examples. So learning can take a very long time for large scale problems. So for the summary of classifiers which we went through, the nearest neighbor and k nearest neighbor classifiers, they use the distances. And for support vector machines, it is a kind of a linear classifier which has margin maximization. It also uses the kernel trick, and it can use different kernel functions. It can deal with multi-class problems, and of course there are many classifiers out there such as neural networks, boosting, decision trees. We'll look at one of like two of those just in an abstract way. So this is an example of a decision tree. A decision tree is a flowchart like a structure in which each internal node represents a test on an attribute, for example whether a coin flip comes up heads or tails. Each branch represents the outcome of the test, and each leaf node represents a class label, which is decision taken after computing all attributes. Now, some of the notable decision tree algorithms include ID3, which is also known as iterative dichotomizer 3, C4.5, which is a successor of ID3, and CART, classification and regression trees. CART is the most, it's like the mostly used decision tree algorithm so far. Chi-square automatic interaction detection, CHI, performs multi-level splits when computing classification trees, and MARS extends decision trees to handle numerical data better. Now, conditional inference trees are also available, but they are statistics-based approach that uses non-parametric tests such as splitting criteria corrected for multiple testing to avoid overfitting. This approach also results in unbiased predictor selection and does not require pruning. Now, ID3 and CART were invented independently at around the same time between 1970s and 1980s, yet they follow a similar approach for learning a decision tree from training tuples. It has also been proposed to leverage concepts of fuzzy set theory for the definition of a special version of decision tree known as fuzzy decision tree. In this type of fuzzy classification, generally an input vector is associated with multiple classes, each with different confidence values. Now, boosted ensembles of fuzzy decision trees have been recently investigated as well, and they have shown performances comparable to those of other very efficient fuzzy classifiers. Now, as you will see that here we have to actually come up with the features which are most prominent or which are most effective for making up or like breaking different attributes into trees based on a certain condition. So this particular breakage or this particular selection of these features is done by Gini impurity. One of the methods is Gini impurity, which is actually used by a CART, classification and regression tree algorithm for classification trees. Another attribute selection method is information gain, which is used by ID3, C4.5 and C5.0 tree generation algorithms. And information gain is basically the concept based on entropy and information content from information theory. The underlying methods used to train the classifiers here, let me say you this, that the underlying methods used to train the classifiers cannot be explained in such a short time. Of course, if I want to explain you the information gain, that how it works, or the Gini index, that how it works, I have to show you the computations and how they select some of the attributes to be used for like splitting the tree. But this will require time, so I'm planning to make more videos in the future specific to each classifier after the completion of this semester. So do let me know in comments if you want me to make more videos like this for a specific classification algorithm. So there is another extension, let me say extension, not modification, but extension of decision trees is the boosting methods, which is the ensemble methods. Now, AdaBoost or adaptive boosting is an ensemble learning method, also known as meta learning, which was initially created to increase the efficiency of binary classifiers. AdaBoost uses an iterative approach to learn from the mistakes of weak classifiers and turn them into strong ones. Now, there is another not boosting but bagging method, which is random forest, and random forest is like a kind of a majority voting mechanism for on top of the decision trees. So you apply many decision trees and you take the decisions, and you perform the majority voting, and the label with the majority voting will be selected as a particular label. Now there are of course many variant to boosting methods. The one is AdaBoost, there is also gradient boosting, there is XGBoost, extreme gradient boosting, there is Logistic boosting, there is Rust boost, and there are many other boosting variants which can be used based on your particular use case and application. Now one of the example of this boosting decision trees is that if you will see here the attribute high an image, if yes it is smooth, if no it is green. For the smooth, if it is yes This will again ask the question if it is blue. So if the histogram is of the blue is higher, yes, then it will just consider sky. If you will consider it no, then of course it will just switch to another label. Now here in this case, if the smooth is no, then you will see that this has a kind of a weak relation. So what it does is it sets it as a weak classifier and it will try to train it to make it a stronger one. Now similarly, if in this case, if you will see that many long lines have a yes and very high vanishing point has a yes, then this is a kind of a weak classifier and it will again train it to convert it into a stronger one. So in this case, it is a clear distinction that this will label blue, which is the sky. This is a clear distinction that it will label as green, which is ground, and this needs to be trained more to make it a good classifier for classifying vertical. Now using boosted decision trees can be flexible because it can deal with both continuous and categorical variables. It can control the bias variance trade-off with respect to the size of trees and number of trees. Boosting trees often work best with a small number of well-designed features, and boosting stubs can give a fast classifier. Now, visiting this particular pipeline, we have to understand the concept of overfitting and underfitting with machine learning algorithms. Now, the cause of poor performance in machine learning is either overfitting or underfitting the data. So when you will apply these kind of machine learning, you will discover the concept of generalization in machine learning and the problems of overfitting and underfitting that go along with it. So discover how machine learning algorithms work, including KNN, decision trees, naive Bayes, SVM, ensembles, and much more. But you have to understand that all of them can be prone to overfitting and underfitting. Now, this is a kind of a generalization, which is how well does a learned model generalize from the data it was trained onto a new test set. Now, from elite data science, bias occurs when an algorithm has limited flexibility to learn the true signal from the data set. And Wikipedia states that bias is an error from erroneous assumptions in the learning algorithm. High bias can cause an algorithm to miss the relevant relations between features and target outputs, and also referred to as underfitting. So bias is the accuracy of our predictions. A high bias means the prediction will be inaccurate. Intuitively, bias can be thought as having a bias towards people. If you are highly biased, you are more likely to make wrong assumptions about them. An oversimplified mindset creates an unjust dynamic. You label them accordingly to a bias. Foreman's article summarized this as bias is the algorithm's tendency to consistently learn the wrong thing by not taking into account all the information in the data. Now for the variance, the elite data science says that the variance refers to an algorithm's sensitivity to specific sets of the training set occurs when an algorithm has limited flexibility to learn the true signal from the dataset. Wikipedia states that variance is an error from sensitivity to small fluctuations in the training set. High variance can cause an algorithm to model the random noise in the training data rather than the intended outputs. Variance is the difference between many models' predictions. Unlike the analogy as before, we are implementing complicated models. Hence, any noise in the dataset might be captured by the model. A high variance tends to occur when we use complicated models that can overfit our training sets. For example, a variance can be thought as having different stereotypes based on different demographics. For example, a complicated model might depict people's name as a good predictor of our hypothesis. However, names are random and should not have any predictive power. In one dataset, people with the name Kamran can indicate they are likely to be criminals. However, in another dataset, people with the name Kamran can indicate they are likely to be graduates. Hence, names should not be used as a predictive variable. So Formans describe variance as the algorithm's tendency to learn random things irrespective of the real signal by fitting highly flexible models that follow the error noise in the data too closely, and is also referred to as overfitting. Now, if you have a simple model, you might conclude that every Kamran are amazing people. That represents a high bias and low variance problem. Your dataset is biased towards people with the name Kamran. Thus, most predictions will be similar since you believe people with Kamran act a certain way. You attempt to fix the model, however, the model is too complicated. Your model has different results for different groups. Thus, Kamran can be a wonderful person, a criminal, an athlete, and a scholar. You must find balance. The good thing, if you do cross validation, you can train on many datasets and average their predictions. Unfortunately, you cannot minimize bias and variance. So there are some categories to it. One is low bias and high variance. A low bias and high variance problem is overfitting. Different datasets are depicting insights given their respective dataset. Hence, the models will predict differently. However, if average the results, we will have a pretty accurate prediction. For high bias and low variance, the predictions will be similar to one another, but on average they are inaccurate. So generalization error affects, of course, the underfitting, which is the model is too simple to represent all the relevant class characteristics. So in this case, if you will take the blue line is quite simplistic to fit these points. But if you kind of consider a quadratic line like a second order degree polynomial, you might get a good representation of the data points which have been shown here. So blue line refers to the underfitting problem. Now it has a high bias, which is few degrees of freedom, and low variance. It should have high training error and high test error. Now for the overfitting, the model can be too complex and fits irrelevant characteristics, that is noise in the data. Now in this case, a green line is a good representation where a blue line fits exactly all the data points, tries to fit exactly all the data points. But in this case, if I have a certain kind of, like, if I say that I have a point here, maybe it could not identify this point, or maybe it could not identify this point, or maybe it could not identify this point, because it is quite overfitted model. So this is also referred to as overfitting. It has a low bias, many degrees of freedom, and high variance. It has a low training error and high test error. So if you consider a famous course from Andrew Ng's, which is machine learning course on Coursera, he says that if you have a high variance problem, you can get more training examples, because the larger the data set is more probable that you to get a higher prediction. Try smaller sets of features because you are overfitting. Try increasing lambda in terms of regularization, so you cannot overfit the training set as much. The higher the lambda, the more the regularization applies for linear regression with regularization. And for high bias problem, try getting additional features. You are generalizing the data sets. Try adding polynomial features, make the model more complicated. Try decreasing lambda, so you can try to fit the data better. The lower the lambda, the less the regularization applies for linear regression with regularization. Of course, this is also true for other machine learning algorithms. Now for more explanations of bias variance, you can also refer to this books, which is Neural Networks book. So from the link above, you can only get generalization through assumption. Thus, in order to minimize the MSE, we need to minimize both the bias and the variance. However, this is not trivial to do this. For instance, just neglecting the input data and predicting the output somehow, for example, just a constant, would definitely minimize the variance of our predictions. They would be always the same. Thus, the variance would be zero. But the bias of our estimate, that is the amount we are of the real function, would be tremendously large. On the other hand, the neural network could perfectly interpolate the training data, that is, it predicts y equals to t for every data point. This will make the bias term vanish entirely, since the E of y is equal to f. But the variance term will become equal to the variance of the noise, which may be significant. You can also learn more of these things in the chapter 9 of Bishop and the Jeeman et al. Paper. So, in general, finding an optimal bias variance trade-off is hard, but acceptable solutions can be found by means of cross-validation or regularization. Now, one thing which I come across the most is that which learning algorithm or the which supervised learning algorithm to apply. So let me tell you this, that there is no classifier which is inherently better than any other. You need to make assumptions to generalize. And there are three kinds of errors, which is inherent, which is unavoidable, bias due to oversimplifications, and variance due to inability to perfectly estimate parameters from limited data. So this phenomenon is also referred to as no free lunch theorem. The two well-known theorems bearing the same name, one for supervised machine learning and one for search optimization, the thing that they share in common is that they state that certain classes of algorithms have no best algorithm because on average they'll all perform about the same. Mathematically put, the computational cost of finding a solution averaged over all problems in the class is the same for any solution method. So no solution therefore offers a shortcut. So you can get a generalization through assumptions only. Now, one thing, let me explain you the difference of deep learning with the shallow learning, which is we discussed about the machine learning algorithms. They are also referred to as shallow learning. So let me tell you the difference of the deep learning with the shallow learnings with a very abstract example. So for standard computer vision systems, we get an image, we extract the features, let's say hog, we extract the mid-level features, and then we apply the classifiers such as support vector machines on any other. Now for deep learning, we get an input image and the whole process is end-to-end embedded in an end-to-end training. So it's like it will automatically extract the features, mid-level features, and then learn to classify different examples. So this particular deep learning strategies can be applied to unsupervised learning as well as reinforcement learning. So if we see standard reinforcement learning, you extract the features. I don't know which features, some of them may be just different color pixel values, and then we extract more features. Exactly, we do not know yet because it depends on the application itself, and we drive a linear policy or value function to drive an action. But for deep reinforcement learning, this whole process gets automated in an end-to-end way to drive an action. So this is the difference between deep learning and the shallow learning algorithms. So there are many classifiers to choose from. You can choose from k-nearest neighbor, SVM, naive Bayes, Bayesian network, logistic regression, randomized forest, boosted decision trees, restricted Boltzmann machines, neural networks, deep convolutional network. But if you will ask which is the best, I will again refer you to no free lunch theorem. Now there are some claims which I want to just clarify. The decision to use machine learning is more important than the choice of a particular learning method. But of course, with an exception to deep learning, because it learns the feature representation itself, and there is the unreasonable effectiveness of data because the deep learning requires a large amount of data. What to remember about classifiers? There is no free lunch. Machine learning algorithms are tools, not dogmas. Try simple classifiers first. Better to have smart features and simple classifiers than simple features and smart classifiers. Use increasingly powerful classifiers with more training data. Bias variance trade-off. So this is all for now for introduction to machine learning. I have explained you in a broad manner, in a like more abstractive manner, that what are the machine learning algorithms, how they are applied to classify the data or categorize the data with respect to the labels which have been provided. So basically, uh, I will not discuss more on regression problem because they are more or less the same. Of course, they deal with the continuous data, but the process is more or less the same. So I will leave it to just the supervised learning with the categorization and classification problem. If you have any questions, then of course you can leave the comments, or you can ask them on Google Classroom, or you can just ask me live in the live session which we conduct every week. And of course, let me know if you want me to make videos for specific machine learning algorithms and go into the details of the computation of each classification method. Thank you.